Welcome to Spring LIB.
So in part A of this problem, we are supposed to figure out how far block B will travel after the collision with a coefficient of friction of 0.1, where A has a smooth surface, so it won't. Block A has a smooth surface, so block A will not experience any deceleration, only block B will. So in part A, this is a completely elastic collision. So the first step is to figure out the velocity of block B right after the collision. So we're going to use conservation of momentum. We're going to have the momentum of A, which is the only momentum. That's going to be equal to the momentum of A after plus the momentum of B after. Now, since their masses are all the same, we'll just call that m. So this is m times 10 meters per second. And it's going to be m times v1, which is going to be the velocity of A after the collision, and m times v2, which is the velocity of block B after the collision. Now the m's will cancel because each term has one, so we end up with v1 plus v2 is equal to 10 meters per second. Now we also know from our text and from the collision equation, when we have a perfectly elastic collision, that v1 plus v2, sorry, minus v2, excuse me, after the collision is going to be equal to minus v1 minus v2 before the collision. And since v1 is 10 and v2 before the collision is 0, we're going to end up with v1 minus v2 is equal to negative 10. And this is after the collision. So this will be, we'll call this equation number 1 and this equation number 2. And if you subtract this from this one, we got v1 plus v2 equals 10. Here we have v1 minus v2 equals negative 10. Well, if you subtract this equation from this equation, you should end up with 2v2 is equal to 20 meters per second. Or in other words, v2 is equal to 10 meters per second. Now, B does not continue at that speed. It's going to decelerate. And it's so it'll have a friction force that is equal to mu times the normal force. And using the work energy theorem, we can see that the kinetic energy needs to equal the friction force times the distance traveled. So it's going to be mu mg times d, where d is the distance that this thing travels. Well, there's an m on both sides, so that cancels out. So we've got 1/2 v2 squared is equal to mu times g times d. If we solve that for d, we're going to get 10 squared, or 100, divided by mu, which was 0.1, times g, which we are told we can use 10 for, times 1 and times 2, because there's that 1/2 there. And so you'll get 0.1 times 10 times 2. On the bottom, you'll end up with 2 again. So 100 divided by 2, you end up with 50 meters is the distance traveled. Now, part B of this problem asks us to consider if this was perfectly inelastic. So when things are perfectly inelastic, then they're going to stick together. So from conservation of momentum, we're just going to have momentum of block A is equal to momentum of block A and B afterwards, because they're going to stick together. So this is m times v of A, which is 10 meters per second, and then 2m times v, which we'll call this, we'll just leave this as v. This is 10. So the m's, of course, are going to cancel out. So we have v is equal to 10 over 2, or 5 meters per second is how fast block AB system is going to be going after they collide. So from here, we can use the work energy theorem again, and we know that the friction force is going to be equal to the coefficient of friction times the normal force, where this is now going to be 2m. That's a 2, because we have more mass since they stick together. And so we have our kinetic energy, which is 1/2 times the mass times the velocity squared. Set that equal to the force times distance. So that's 2 mu mg times d. The m's will cancel out. Let's use red for that. This is 2 times 1/2, so those cancel out. We have v squared, which is now 5, so this becomes 25 meters per second. And 2 mu g times d. So if we solve for d, we should end up with 25 divided by 2 times mu times g. And we were told that we can use 10 for g. So it's 2 times 10, or 20, times 0.1. So 2 again. You should end up with 12.5 meters.